Morning, guys. So let's now study uh, the analysis for laterally unsupported beams. So in the laterally unsupported beam analysis, we need to find some additional properties uh, that relates to lateral support condition. So these are actually the LP and the LR properties. Okay, so these are sectional properties, which are the factors to be used in order to determine whether or not the beam will exhibit a lateral torsional buckling behavior. And these limitations were based on the concepts and theories involving uh, lateral torsional buckling, which I have presented on a video involving some mathematical derivation of the values of LP and LR. So the LB parameter here is the actual unbraced length, okay, which you are going to compare with LP and LR to determine whether your section is critical as far as lateral torsional buckling is concerned. The other properties or parameters are all common to all of us. They have been used in the lateral supported beam analysis, uh, including MR, which is the residual moment that is used to represent the resistance when your beam has achieved the limiting value for lateral torsional buckling. So the graph for the moment strength curve, therefore, constitute a moment versus lateral support requirement, which has the same shape with that of the compactness graph for moment versus lambda. The only difference is that the limiting values at points of critical moments here are called LP and LR. Although there's a point here, LPD, which exhibits a limiting value for your lateral support length that will give you, or that will allow the beam to achieve full plastic behavior when this value has not been exceeded. Okay, so later on we will try to plot this to determine the moment strength considering lateral support conditions. So our regions will be, of course, your plastic, okay, your inelastic and your elastic region. So buckling may occur here in the inelastic or the elastic region, or it can happen that no buckling will occur when your lateral brace and brace length does not exceed LP. So to be specific on the formula, we shall now define your moment values, MP, as your plastic moment, which has a formula Fyz. The same is true with your compact requirement, but it shall not exceed a limit equivalent to 1.5 Fy. So this value has something to do with the shape factor for weak axis bend. Okay, so in order for us not to achieve an excessive working load or overestimate the capacity, we only need to limit our uh, m sub p uh, within the value of 1.5 my. Of course, my is equal to Fy Sx. M is the controlling combination for the factored load moment. Mn is the nominal moment strength. Pb is the reduction factor for beams, which is 0.90. And as I told you, your 1.5 here simply refers to the ratio of C over S, which is your shape factor. So for the design criteria in LRFT, we take note that the required moment strength must be less than or equal to the design strength of the section, or simply your resistance must be greater or equal to your moment load Q. And in order to calculate the nominal moment strength Mn, we need first to calculate again these two properties, LP and LR. Okay, so these are additional section properties in excess of the properties you may be obtaining from the table, or you may be computing using basic calculations. So LP is simply equal to 1.76 Ry square root of E over Fy, and LR is simply equal to Ry x1 over Fl square root of 1 plus square root of 1 plus x2 Fl squared. So they are both sectional properties. And the values of course, your Ry here is simply your radius of gyration in the lateral direction. So not necessarily the width, no? While your x1 and x2 are additional properties you can have from the table. In case it is non-standard section, you can use a formula. So FL has something to do with the comparison for a hybrid section. So a hybrid section has the elements specifically different in terms of the web and the flanges. So MR is simply equal to FL/x, where FL is Fy minus Fr, wherein the value of Fl is the smaller. Okay, so when we're now talking of a we're talking of a non-hybrid member, so you use simply this formula. But when you're talking of a hybrid member otherwise, you have to choose between FYF, the flange yield, or simply your web. Okay? Okay, so for the web, you don't have to reduce the yield strength with Fr, but for the flange, you have to reduce it and choose the smaller value. So take note that Fr is simply the assumed residual stress in compression, which is 10 ksi for rolled shapes and 16.5 ksi for welded shapes. Now, in the new AISC, there is some modification on the value of Fr, okay, and Fl. So I will give you the update on this later so that you will not be confused, no? In case we apply it on sample problems. Okay, for x1 and x2, as I've said, if you don't have a standard section, you have to compute, no, the value of your property, where x1 has something to do with your uh, elastic property. Okay, elastic properties, and x2 has something to do with your torsional properties. So, ito, may konting, ano ito, relation with your elastic shear properties and elastic torsional properties. Okay? So you can compute it on this basis. Of course, the units must be consistent for you to be able to find the right value for your moment strength. You have to come up with a consistent unit. And if we are using an English unit, so this must have something to do with inch kip unit. Okay. Okay. So if I'm going to make a unit analysis here, E is in KSI, and then G is also in KSI. J is in inch cube, is polar moment of inertia. Okay, sorry, inch to the fourth. Then A is in inch squared. Okay, so in the numerator you have actually a kip squared over inch to the fourth. So inch to the fourth, inch squared. So you can cancel inch to the fourth and inch to the fourth here. Okay, so what remains is kip square, inch square, but you have a square root sign there, so you only have a kip inch. So if I divide this by an inch cube, okay, so this is an inch cube, so my final unit for this is in kip per inch. Okay, squared, I think it's KSI. Kasi na square root pala to, no? This is inch square, squared is kip inch. Okay, so kip per inch. So kip inch, sorry. So this final is in, if you take the square root, this is in kip inch. Okay, so if I divide this by inch cube, so kip inch square. Okay, or simply this is in KSI, while x2, okay, is equivalent. This is CW is in inch to the 6, I think, and this is inch to the 4th. Then I multiply it by inch cube over K. G is a KSI inch cube. So this is kip per inch square, then inch to the 4th. Okay, so what happens? So this becomes 2, I mean, inch square. So this becomes inch square. So cancel ito, no? Cancel yan. So ang matitira ito na lang. So this is inch cube sorry, square pala to class. So, square to. So, may matitira pang inch square dito, no? So, this becomes uh, inch square. Okay, so this cancels out. 2, this is inch square. So inch cube and inch square will be inch. So inch square, this is inch to the fourth all over cube. Okay? So, kasi 2 na lang ito yan. Inch square. Okay, so this is the unit for x2, and this is the unit for x1. So we'll check that on that later. So notice this Sx, Iy, and Ry are simply the same parameters we use in the laterally supported procedure. So for the choice of the formula, if the shape is compact, meaning to say that lambda is less than or equal to lambda p, we don't need to check for the flange local buckling and web local buckling. We directly solve lateral torsional buckling effect uh, by using these 3 cases. We have a case 1, case 2, and case 3. Okay. If LB is less than LP, no lateral torsional buckling, then we simply use the formula for MP, but not to exceed 1.5 Fy. So this will be directly solved by using a ZFY formula. If LB is in between LP and LR, this is now an inelastic lateral torsional buckling, then we are forced to do some interpolation, okay, on the value. So we simply interpolate here. So this formula has something to do with this interpolation formula here, okay? Wherein the critical point we are going to use is, of course, your MP here, your MR, your P, LR, and of course your unknown value of MN for a particular LB. Okay, so this is the point at which your interpolation formula is determined, but not less than, or sorry, not greater than MP. So if LB is equal to LR, then we are forced to solve your MN in terms of a critical value, MCR, uh, here. Okay, so this is now your MCR value given in this formula. Medyo mahaba, no? So you can use either this formula or this formula. Again, some updates on the AISC will be given to you later. Where MCR, take note, is a nonlinear function of LB. Okay? So I'd like to look into the value of a CB here. So there's an additional parameter here known as the moment modification factor, which is something to do with the moment gradient. Okay, so we need to find what moment gradient is all about uh, in another lecture video. So CB is a factor that takes into account a non-uniform bending moment distribution over the embrace length. So CB is something beneficial rather than detrimental, no, to the value of your capacity. So this is always greater or equal to 1.0. MA is an absolute value of a moment at quarter point of the embrace segment. MB is the absolute value of moment, the midpoint of the embrace segment. MC is the absolute value of moment at the quarter point of the embrace segment. And Mmax is simply the absolute maximum value of the entire moment diagram. So this formula there's an alternative to this formula. I call this the new formula, although it's not no longer new. We have also a parabolic formula. Okay, parabolic formula, which is a very old formula to compare with. So in our example problem, I will introduce to you the formula for comparison, for the sake of comparison. For now, let me end my lecture on a laterally unsupported beam at this point. Thank you very much for listening.